Um, so we'll go ahead and get started. So first off, thank you, Kristen, for agreeing to come join us and speak, even on this virtual platform that we're all kind of acclimating to these days. It's my pleasure to introduce Kristen Grauman, who's a CVR Vista speaker for today. She's a professor in the Department of Computer Science at University of Texas, Austin, and currently on leave as a research scientist at Facebook AI Research. Her research interests are in computer vision and machine learning with specific focuses on visual recognition and search. She received her PhD from MIT, and throughout her career, she's received a large number of awards and honors and done an incredible amount of work. I don't have time, and I don't know that it would be helpful to go into all of it, but she's a Sloan Fellow, and she's won NSF Career Awards, ONR Young Investigator Awards, several paper awards at computer vision conferences throughout the years. She's currently serving as an associate editor-in-chief for PAMI and on the editorial board for the International Journal of Computer Vision. She's served as program chairs for CVPR and NeurIPS, and any number of other awards and honors, along with a stellar body of research to her name as well. So it is my great pleasure and honor to introduce Kristen, and thank you and welcome, Kristen.
Okay, thank you very much. Thank you for the nice intro, and thank you all for being here to allow me to share some of our work. This talk is about people watching for agent learning, and to set the stage, we're thinking of problems in terms of embodied AI, so right at the interface between computer vision and robotics, where we know very well that there's such a great need for agents that are able to learn and have multimodal perception, but do so very much in the context of action and interaction in the world. And this spans any number of applications, such as navigating in new environments, performing search and rescue, or applications in augmented reality as well. Now, in this space of problems, we're particularly interested in agents that can operate in human environments. So agents that could, answer a question and act on a request like, could you heat a cup of tea and bring it to me? This means an agent has to do a number of, let's say, more traditional perception tasks that remain quite challenging. Things like how to move around the space, decide what a cup looks like so you could find it and retrieve it. And we can think of this space of problems as things that fall into traditional recognition and navigation. So knowing what things are and knowing how to move around. But of course, there's also a layer of problems in a request like this that go beyond those tasks, and they're tightly integrating between perception and action. So one, for example here, can the cup be heated? Which cup could be heated? Where would I go to heat it? Or once we get to manipulation, how would I grasp the cup to do it? And so these are all problems that go in hand with the above, but now require us to not just know what to call things, which we in computer vision have become increasingly better and better at, but also how things work and how to interact with them. So in this talk, I'm talking about our efforts in that second set of problems, trying to move towards ways to bring in core perception to aid in answering such questions. So the part of the work I want to share today is motivated by this question of how do you teach an agent? Very fundamental question, tackled in a lot of different ways. And when we think about today's embodied agents, they're able to learn, for example, just from direct experience, so being able to interact in the world and find out how things go and get better and better, but also through human teaching, so often from a demonstration, even a kinesthetic demonstration in which a human teacher, like the one on the left, can instruct a robot how a task should be done. Now, vision is, of course, quite prominent as well. However, often we're thinking of vision as a sensory modality, so a way to sense and measure what's around the agent. And what this talk is about is thinking about pushing even further in terms of what we can learn from people, in particular to be able to learn how to act by watching people. Here I'm showing you an egocentric video captured with a head-mounted camera on a person going about some shopping mall activity. And I think this example highlights well how watching video, watching people in their own natural habitat can allow us to pick up things about motion in the environment. How do you navigate through it? How does a person direct their attention, including when they're doing a task? how does a person interact with other people? And as that clip is just showing, how do they interact with objects? All these things would be rich things that we would like to pull from human behavior as one source of direct learning about how the world works and how we can operate within it. And if we can do this, then we'll have influence for a number of embodied perception tasks falling within mobile or manipulating agents, robots, autonomous vehicles, and again, even augmented reality. Okay, so that's the big picture. We want to explore people watching for agent learning, and this will allow us to move towards intelligent embodied agents that can learn by watching how people interact. And there's two dimensions of this interaction I want to cover today: the environment and objects. So on the environment side, we'll be thinking of spaces not as something to only move in and measure and map, but also spaces from which we can understand how things work or where particular activities are likely to succeed. And then in the second part, I'll talk about objects. So here we're thinking of affordances of objects at a more fine-grained granularity so that we know how to touch them and use them. And in both cases, we're trying to look into ways in which video, and especially egocentric wearable camera video, can allow us to learn these things. So let's talk about the environment. So here I'm showing you a top-down view of some 3D space. And a very fundamental question is, well, how do we map a space? And one way, certainly, is to map it in a metric manner to do some kind of reconstruction, either 3D or 2D, to know where things are. We can also think about mapping in a semantic manner, so not just to know where all these surfaces are, but what are the main objects? What are the main room types? Now, what we want to consider here in the context of this motivation of learning from how people do things is instead to map a space by its functionality. Okay, so we want to be able to look at a space like this and anticipate where a person or an agent can do any number of different activities, like where's a likely place to sit, where could I exit, where would I hang something. Now, I said that egocentric video is a really neat key to try and unlock this kind of representation of an environment. Here's another egocentric video from a person doing kitchen tasks, and we can see that this video is very special for giving us that first front seat view of a human's actions in the world, including hints about their intentions, their goals, and how their changes in the environment are trying to affect those. So for example, here, we can look at such a video and try to learn what will he do next, where are these areas for the key activities, and then how is this space usable now or later. So the first key idea that I wanted to present, now that I've kind of set up this stage here, is our new video model called Egotopo. And this is where I'm trying to answer that question of how to map a space and to do so with learning from human egocentric video. Now here's the key idea, is to map an egocentric video into a topological map that is grounded in how people use a space. So rather than think of the video as simply a stack of frames on which to do some 3D convolutions, say, we'll think of it as a topologically organized series of activity zones, so places where coherent sets of objects and activities happen. Okay, so we'll walk through the video and compose a graph like this, and then I'm going to show you in the coming results what this will allow us to do in terms of understanding the affordances of the environment and how to plan new activities. So in particular, the two key things that we want to get out of this topological encoding of the video is to allow ourselves reasoning about the first person behavior. For example, through such videos, we may learn that after visiting the refrigerator and getting a vegetable, it tends to go to the cutting board and then later the sink. And then the second thing is to allow reasoning about environment affordances so that we could look at a portion of video or a new frame in a new environment and anticipate which of any possible actions are going to be most likely. So let me say a bit about how this graph is constructed. First, we have a localization network that's going to decide when frames belong together in a node of the graph. And it'll be based on both traditional metrics that say how visually similar frames are or how consistent they are in terms of their geometry, but also cues that are coming from the camera wearer themselves in terms of the proximity and time of the different frames, as well as the predicted action and object distributions in a frame. And so this localization network is a model here, a Siamese network that could take 2 frames and decide if they're similar or not. And it's trained by these cues that I'm showing here. Once we have this localization network, now go in a forward pass through an incoming video and decide for every frame whether it belongs in a node that exists or needs to form a new node. And so here is where we're linking different time points of the video according to consistency in visual appearance, geometry, but also the human use. Okay, so maybe here, this frame down below was similar enough to join a node that already exists. Now, after you've done this process, what you have is this connected set of nodes, connected in terms of the adjacency of human visits. And at each node is a list of small video clips that are the visits of that camera wearer to each of those nodes. Here's one such graph being constructed. The input video is on the right. It's being shown in a sped up manner. And here we see on the left the different nodes of this graph emerging as the person does some daily life activity. These are all videos from a recent data set called Epic Kitchens that has people doing unscripted activities in their homes, in their kitchens, for 30 to 50 minutes at a time. Okay, so for one video, we can start by comprising such an Egotopo graph. Now, once we have this encoding, we care about tasks, as I mentioned before, in terms of affordances and use of the environment. So I'll show you that in 2 different tasks. The first one that we attempt is to perform action anticipation. This is a task of not saying, what do we see happening now, but what do we expect will happen next? You can think about how intelligent agents or agents that are trying to assist we humans in our activity would need to know ahead of time what's the likely event, not only what's happening now. Now, we're considering this in particular in a rather long-term horizon. So existing challenges have been built around kind of predicting what's the next second of activity. Here in this experiment, we're going to consider future actions that can span anywhere from 5 to 45 minutes. So if you think of the whole video, now as input, we'll get the first K% of it, and we'll need to predict all the actions that happen in the remainder. And then you can just slide that K back for evaluation. So you can think that to solve this well, to know what are all the remaining activities or actions that should happen in order to complete what was begun at the start of the video, would require a structured and rich encoding of the activity information. This is the hypothesis, and we'll be testing Egotopo to see if it can have some advantage here. So to do it, take the graph representation I mentioned earlier, construct it from any video, and now we'll have a node level representation for all of the clips that had occurred associated with that node. Then at the graph level, we'll aggregate those node level representations using a graph convolutional neural network. Now this network, on top of this network, we're training a classifier to do that anticipation task, to report back the multi-label answer for what are the next actions that are likely to occur. Okay, so for this task, here I'm showing you some results where I'm looking at the dataset Epic I mentioned previously, that's on the left, and EGTEA, which is a Georgia Tech dataset, also in Kitchens. And these are accuracy rates, the mean average precision for performing that anticipation over all the different actions. And so higher is better here. The things we're comparing to are more off-the-shelf pure video methods, meaning those methods like i3D and others that think of the video as a stack of frames to find these consistent appearance or motion patterns. And then below that, a chunk of methods that are also doing more complex structured encodings, in particular in terms of their temporal aggregation, like ActionVLAD, videograph, timeception. Now overall, the Egotopo combined with the GCN is giving some strong performance relative to these. And in particular, more than 2 points better than the best method for this Epic Kitchens challenge. Okay, so this is an encouraging result for saying that if we think of an observation in this space, not solely in terms of what we saw, what was over the course of the video frames, but instead if we think of it as grounded in a 3D space that is shaped by where people tend to do different activities, then we can enrich this kind of anticipation task. All right, so the second task here that I wanted to show is related but a little bit different. So here the question is, can we look at a portion of video and predict all interactions that are possible? So say, look at this frame and say, what are all the interactions I could do here? Now again, in training video, you may or may not observe all possible actions there. For example, maybe here I've only observed someone turn on the stove, when in fact there's an array of things that could be happening in this space. So here's the idea we had to enhance Egotopo towards tackling this challenge. It's to think of these topological graphs as not being limited to a video at a time, or even a single environment at a time, but to link these graphs from one environment to the next. So for example, if I had an Egotopo graph in Kitchen 1, then I can link nodes to Egotopo graph from kitchen number 2 according to their relatedness and functionality. So nodes that share action and object distributions. So this linking is important because it allows us to essentially propagate labels that we have not observed in one environment from another environment in which we have observed that label. So for example, kitchen 1, I never saw someone mix stock at the stove, but in kitchen 2 I did, and because the nodes are linked, now we can propagate the labels from those graph instances to the other. So this is what we did in order to address the environment affordance prediction task. And what it means is you can now take a frame of this video and report back a distribution over the possible actions for saying which are more or less likely. So for example, on the right, looking at frames like this, the prediction is that pouring water is very likely. And the mixing stock is less likely. Okay, so quantifying performance on this, again, the same data sets. Here we're comparing to baseline methods that would treat this in a pure 3D way, meaning perform structure for motion, look down across the map and do label sharing, but now rather than do it in a functional way as I described, the baseline would do it based on just 3D proximity. So sharing labels across the same points in space that are nearby, or a baseline that does the same, but only in terms of visual similarity. And again, these are encouraging results that we can get more robust affordance predictions through this structured encoding. Okay, so this is Egotopo in summary. Here we're just seeing another example graph and the affordances that were gleaned out of this video. And overall, what this is offering is a step towards a structured representation of video that's very much grounded in human use of a space. So kind of thinking of video not as a stack of frames, but as something that is both grounded in the space around a person and organizable according to how they use the space. Okay, so moving from here, I want to take one more example from our current work to talk about environments before we move on to objects. And if you think back to that example I started with, this question, how do we as an agent learn to address a request, like could you heat me a cup of tea, bring it to me? There's some exciting work going on to address just this kind of challenge in embodied AI, both on the robotic side as well as people working in simulated environments with photorealistic or renderings. Now, what do you do, say, taking a learning-based approach, maybe by imitation or reinforcement learning? You can imagine learning a policy that handles that task very well. Okay, so the agent learns exactly how to perform the task of heating tea and even generalize to new environments to do so. But that will be a specialized policy for that task, and it'll know about finding certain objects and doing them in a certain sequence. So what happens then if you have a new task, like I want you to hang the clothes to dry? Of course, under that kind of regime, you would train another policy to do this in a task-specific manner. So looking at that scenario, we're interested to know if we can move more towards task-agnostic learning for interaction. And I'm going to motivate this very loosely with a mental device that helps me, which is thinking of an infant just developing its ability to understand the influence of its own actions in the world. Okay, this infant comes not knowing what objects are, how they're separated, what they'll do when different motions are taken, and yet these things are exactly discovered through its own interaction. So we can take this as a mental model of what we would like for our agents who will come into these new spaces without yet knowing exactly how they work, and yet will be able to, as I'll show next, translate task-agnostic kind of behavior in order to understand, fiddle with, play with, interact with the new things in new spaces. Okay, so that's the goal. Now, in particular, we're talking about trying to learn a task-agnostic policy that'll guide an agent to attempt unfamiliar actions in unfamiliar environments. And we call this problem interaction exploration. Interaction exploration to distinguish it from, say, navigational exploration, in which we want to know the whole map of a space. Here we want to understand the space, but we want to understand it in the context of what we can do where. Okay, and in this work, we're leveraging an environment called Thor, and the images you'll see in the following are from that environment. So here we have a mobile robot who can not only move in the space, but can also move things, touch things, push buttons, turn dials, etc. And what we want is that in a task-agnostic manner, that this agent be able to look at a new space and quickly identify the things that are possible there. Again, thinking of the infant who, once well versed in that toy, would understand for that or a new toy, what are things to try in order to do a successful interaction. If this is learned well, and if it is generalizable, then in an unseen environment, it won't be an exhaustive search to find out how to use it. It will be a more targeted search in terms of finding where these interactions are possible. So this is the main idea. Now to do it, what we'll try is to train a policy in which an agent is rewarded for the number of new successful interactions it completes. Okay, so we're going to learn a policy, train the agent to favor sequential decisions that are made such that it explores the space fully in its interactability. Now, in our case, the visual what we're trying to achieve is a visual affordance model that allow us to guide the agent to do this rapidly. And if to the extent we can do it, the good things we think that can come out are, one, the agent will have a prior of what actions it can do where, getting it ready to then do, two, downstream tasks. So to walk into the new environment and be ready to use it for a task that unfolds anew. All right, so to say more then about how we're going to attempt this, there's kind of two things that can work nicely together, and this is what we want to explore. So the one thing is that exploration, moving about, trying things, is going to help build an explicit visual affordance model. So an agent will find out where things did work, like opening the fridge succeeded over here, and that'll give it a visual prior that can get stronger and stronger about what things look like that are openable. So maybe not just the fridge door, but the doors of the cabinet. Same thing for toggle. Now the other key thing that will work in concert here is that if we do have a visual affordance model that's accurate, that is going to be the thing that can steer an agent towards the regions of the space where its actions may succeed. So rather than blindly trying to open every voxel of space in this environment, we'll be drawn towards doing this in parts of the environment that look openable. Okay, so those two things work together, and we're going to try and train them in concert. So it looks like this. So I mentioned the objective will be, to learn a policy for this agent's behavior that is rewarding it for trying new successful interactions. And why can an interaction fail? Well, because you could say, the agent could say cut when it's standing in front of the coffee maker, and that just won't work. But it could say cut in front of the bread, and that will work. So This is the reward function, simply like a novelty reward for these new interactions. And so if it's an interaction action, meaning not a navigation action, but an interaction one, then it's rewarded first time it's successful with a new object. And so now we'll be training a policy with this reward for the agent to perform across environments. So now let's put these together then. The visual affordance we need to place into this policy learning. So imagine this agent unfolding this episode of interaction with the environment. It tried some things that didn't work. Here at this point, it tried to toggle, and it did work on this coffee machine. And so what the visual affordance model will do is to work backwards in its episode to mark visually those places that correspond to the same one where it had the successful interaction. So in this case, it was a coffee maker, and so you can think of this as like a paint gun. So going back, over different viewpoints it experienced before, it can still register that those were successful places for this action, even though it didn't try that action from that particular position in the environment. So this is going to allow us to train an affordance prediction model, which, given a frame of video, can predict where in the frame is it likely possible to do any given action. And we've got a little helper here, but I'm not sure how much you're ready to help. So this we'll call FA. This is a CNN that's doing image level prediction of affordances, in this case learned from experience. So here is such an agent in action where you'll see yellows and greens popping up, and in the top left are the actions it's trying. So again, some of them work, some of them don't, and our agent's going to slowly learn, or quickly learn, we hope, how to have more of these green successful interactions rather than the failed yellow ones. But for every success or failure, we're getting feedback for this visual affordance model to say what are the visual patterns that are going to allow you to achieve the action you're trying. And this is over an array of, say, dozens of actions. Okay, so you have then a model to go from RGB to a map, one map per action type, so one for put, one for toggle, one for take, etc. And this is connected to the policy learner. And remember, that's the policy learner that's trying to maximize its exposure to successful interactions, such that it walks in a new space and does small number of things, but many of them are successful interactions. Okay, so we'll train these jointly, and I mentioned earlier why they're mutually beneficial, right? One can speed up the other. And so that means now as the policy is executed, it can start to better and better that affordance model and vice versa. In one moment. Okay, I'm sure it's not the first time for anyone where COVID working conditions can alter the course of a talk, but hopefully we're good for now.
Definitely not the first time for anyone, and
Yes.
very much okay.
So here is a video of the whole thing in action. And in this video on the left that I'm about to play, you'll see the egocentric view. This is the stream of RGB frames that the agent sees. And on the right is a top-down map, which the agent doesn't have, but we're just allowed to kind of peer down and see what it's doing. And what you'll see on the left is, again, the actions it's trying in the top left, and the reward it's achieving in the bottom right are. And then on the right, you'll see green and yellow dots, and that means the same thing as before, whether it succeeded, trying something, that's green, or if it failed, which is yellow. So you want more green dots, fewer yellow ones. And on the left, we'll also show the visual affordance map as it keeps getting computed. Okay, so here it is. In this environment, you can see just a handful of the verbs that it knows about, where things might be placeable, toggleable. The countertop is often looking placeable, meaning you could place something there. Coffee maker looks toggleable after a point. Drawers and doors start looking openable. And then on the right, we can see how, despite the fact this is the first encounter with this environment for the agent, it can quickly get to work and figure out how it can be used. Now, in what I've shown so far, this is kind of the part where an agent's learning from experience and building up this visual affordance model. Where we want to go next with this is to make explicit that bridge between kind of work I said earlier in the talk, like with Egotopo, where these affordances are being ripped out of human video without an agent yet in the picture in order to come in with an affordance model even before any experience happens that's able to make these kind of colorful maps. Okay. Now to give you a sense, if you were to train an agent instead to favor novelty, but and so just visit many parts of the environment and then cycle through its interaction vocabulary, you'll have much fewer hits, right? Because it's not drawn in any particular way to go to a space where an action is likely to succeed. All right, and we've quantified all of this in terms of, well, here, how full is the coverage of interactions across time. And so we'd like these to be sharp and high. And we're comparing to a number of things, like some I've already shown. So what if we just randomly moved around and then cycled through interactions? Or if we used off-the-shelf curiosity, which is a intrinsic motivation that says pick things that are hard to predict under your current forward dynamics model, or favor visiting new places, that's what I showed, or favor visiting new objects. And so you can think of those as kind of traditional exploration methods developed sometimes with manipulation in mind, sometimes with navigation in mind. And what we're seeing is that, for these tests, we're getting about 33% more interactions once it's been trained. Okay, so now the final result here is a step towards really taking advantage of this task agnostic behavior. So at this point, what we have is a policy that's agnostic to what the ultimate goal is, but is good at coming into a new space and trying things efficiently, such that it understands the affordance landscape in that new space. And the final step that we want to do here, to start to see its value, is to use that as a prior for a downstream task. In particular, think of that exploration policy as the thing you start with, and now fine-tune or start learning a policy that replaces that exploratory reward with a task-specific reward, so that you can train the behavior to now do the thing you care about. And in this case, we tried 4 different such specific tasks: retrieve something, store something, wash something, or heat something. And if this succeeds, we'll say it succeeds if it's faster to learn an accurate policy for these tasks, having had this single exploratory policy to start. And so that's what these charts are trying to score. On the right, you're looking at the reward versus the number of training episodes. And on the left, we're looking at those 4 different tasks I mentioned against baselines, the same ones I mentioned earlier. And these are success rates, so higher is better. And moderate success in the absolute sense over these tasks, and certainly a clear advantage from having done this prior exploration. Remember, to learn one policy that can then be forked off to be tailored to each of these individual tasks. So there's some evidence of downstream transfer and a lot of motivation for us to kind of work further in this direction, including, as I mentioned, to bridge the video work into this agent-based learning work. Okay, so the second and final part of this talk will be about learning from people at, again, how things work, but in this case, rather than the environment level, at the objects level. And so in a sense, it's just kind of moving down in granularity to individual objects and their parts. So this is a very important problem, and not a new one, but one in which we don't want to solely name an object, but to understand what we could do with it, such as where could I toggle this lamp, where is it adjustable, where could I grasp it. Now, current approaches can do this in a visual learning-based way if they follow a fairly traditional recognition pipeline. So people have explored, what if we ask annotators to label images showing where I can hold this object or where I can push this object, etc. And then we can train a predictive model to reproduce these kind of labels. Imagine a semantic segmentation model that can highlight the regions according to their agreement with that label. Now, this is supervised, so of course it comes with this, at least mild concern that this is rather expensive. But even aside from that, I think a problem here is that there's a little bit of information gap between how people do things and how they think they do them, and how they would tell a system when drawing with a mouse, where they hold a book. So it captures annotators' expectations of what's important. So our idea was to instead allow the people watching to take place here, where we'd like to instead, rather than label images for how the objects get used, simply watch people using objects in video. And as these examples show, we'll do this both in first person video, like on the bottom right, as well as third person. So how can we learn affordances from video, from watching people use an object? The approach that we've developed is going to rely on what's called weakly labeled video. So video where we don't have any kind of spatial annotations saying where these things happen, but we do have videos saying, in this video there is an instance of opening or an instance of pressing for any of the actions we care about. Okay, so we'll start by learning an action recognition model, one that takes a sequence of frames, here in a recurrent neural network, to learn to discriminate between any of the actions that are possible. Okay, so far this is action recognition. But we're going to integrate that with a model that is aiming to anticipate the effects of any one of those given actions. So, for example, in this training instance that was for open, we could look at the aggregated state for a confident frame at which it's recognizable as open. And then we're going to, at the same time in training, require that the model can map an image of the object being used, here it's a microwave, when it's inactive, to that state. Okay, so with this LSTM on the bottom, performing recognition at the top, this is a model that is an anticipation module that knows how to map from an object at rest to that state of where the action is recognizable. Okay, and it's key that it's at rest because the whole point here for affordances is not to say when the action happens, but to say when the action could happen. And that'll be when the object is not yet being touched or manipulated by the person. Okay, so that's kind of part one of the model. Part two is to give back the spatial regions. And here we're relying on what's called a class activation mapping kind of approach, which means we'll go back through this recognition model and identify those regions in the input that are most responsible for declaration of any one of those labels. So for example, here we're saying, where is the visual evidence strongest, such that it would fire for the label pull? And that's via the same anticipation network I just mentioned. And same question, where are the regions in this image that are most responsible if we wanted to know where the action press would be found. Okay, so this will give you then a heat map on the inactive object image that says where these actions are likely to take place. And so for any given input, you'll have a stack of these maps, much like I was talking before in the environment level, where we had affordance maps for each verb. Here, same thing, but now this is just at the object level. Okay, and then before it was through, agent interaction that that model was built up. Here it's through watching the human video. So let me show you this approach at work, and we call it interaction hotspots. Hotspots because we're creating those heat maps to say likely spots for interaction. And we're testing this on two different data sets. So the one on the left, Oprah, is from Stanford, and this is a YouTube data set of people demonstrating how to use different products. The one on the right is Epic Kitchens, and we've seen this one earlier in the talk. Now, a key thing when we were testing this model was to measure how good these heat maps are, not only for new instances, but even for new categories. So that means, what we're aiming for is a affordance model that can look at a new appliance, say, that it hasn't used before, or a new tool, and be able to anticipate how it could be used. And I like to think of the analogy here of, one of us in our friend's kitchen, they're going to have some gizmos or tools or cooking devices that we don't know exactly, but we'll still look at them and have an expectation of how to go about using them or touching them. All right, so let me show you videos first. This is Interaction Hotspots output on some egocentric video where green is mixable, blue is adjustable, and so on the bottom legend there. And here I'm just sampling the verbs that were most frequently observed in this whole data set. There's some on the order of tens of these kind of verbs. And you can see that before the person starts mixing, this looks like a mixable thing. So there's a hotspot there. So does the pan behind it. Over here, there is a dirty knife in the middle that looks washable. There's also a dirty knife on the left of the sink, not being touched yet, but it also looks washable. Here, the pan looks mixable. The jars looked openable. And that door looks openable. And the important thing was that's reported by Interaction Hotspots before the person actually reaches for the door. And the final example, this one on the left, I'm showing state-of-the-art saliency being run, which will find interesting things in the frame, and contrasting that with these hotspots, which are going to be instead indexed by the possible interactions. And this gives us a sense of where we're trying to head with this, right? Seeing the world through the eyes of what I can do where, and learning that from observing in a very rather weakly supervised way how people have done things in the past. Okay, so when we evaluate this, we care again about metrics that say how good are those maps? How accurate are these hotspots? And without going into a lot of detail about this array of metrics, basically these are 3 different ways to score that question. Again, for the 2 data sets I mentioned, Oprah and Epic. And we're comparing ours with some other weakly supervised methods that do different things like saliency or gaze prediction, as well as some strongly supervised ones that do that traditional human labeling. And compared to the weakly supervised one, we're in really good shape. So we're getting a lot of advantage by learning from how people are doing things in the video. And compared to the supervised, we're actually starting to be competitive. So this is an efficiency advantage at least. All right, so one more result I want to show you here, and I think it's perhaps my favorite, about showing where hotspots can go next. And it's to help us understand objects, not only as how they get used, but also for what they are. So we're actually returning to a recognition question of saying, what is the thing in the image? And in particular, we'll be studying this in the low shot regime. So it means you don't have the benefit of thousands of labeled examples. Maybe you have relatively few. So to start, what I'm showing you here are the actual results you get from an off-the-shelf, tried and true ResNet 50 classifier, trying to label the different objects here. And from left to right, it's doing better or worse. It's just fine on the ones of the refrigerator that look rather canonical. It's quite weak on the ones on the right where things just are like unusual in viewpoint or the context is different. Okay, so a traditional model is just going to fail on that right-hand side. Now, our idea is to explore what's known for human understanding of objects, which is that if we can understand how it's used, we're more quick or likely to recognize it. Again, think of yourself in the friend's kitchen with the thing you haven't seen before, but you can kind of guess what it's for, and then all of a sudden, oh yeah, maybe this is a wine bottle opener. So we'd like to bring this into such a recognition system. So what our very first attempt here, very much work in progress, but was to encode these images not just as ResNet 50 CNN features, but also in terms of these affordance maps. So in fact, the feature space of the hotspots that we've learned. And the idea is that this can try to pull out and expose what is shared among examples like this, such as where it can be held or opened in this case. And again, kind of first baby steps, but for a low shot recognition test where we have just 5 labeled examples per class on the COCO dataset, we're seeing a bump in accuracy for doing this encoding. Okay, if we have 3,000 examples per class, that bump doesn't exist, but when we're in this low shot setting, the ability to know how an object works actually helps us be able to recognize it. So I think there's a lot more we can do here to try to bring together this notion of how what object affordances look like, and then how we can recognize new things. All right, so far I have told you about people watching for agent learning, both in environments and with objects. And in this very final piece of the talk, I'm going to continue with objects, and here we're going to make that leap from the image and video-based learning to demonstration through an agent. Now, this is going to be a simulated agent in our case as our first step here. In particular, we're talking about a dexterous robot hand. Dexterous robot hands are going to be quite a challenge to learn for, given the high degrees of freedom that we have, 30 on this particular one. And at the same time, we're very drawn to it because of the relationship and the morphology between humans and this robot. Right? So if we think that there's going to be room to learn how humans do things and let it help our robots, this seems like a good place to start, in that the hands have closer relationships, say, than to a parallel jaw gripper robot manipulator. All right, so this is the domain, and the observation here is that objects are made for human use, many of them, and if we do this kind of visual affordance learning, this will be something to pass on, again, as a starting point for agents to enter the world benefiting from our own experience and our own actions, such that they can learn to do things, grasp objects, do things with them much faster. In particular, this is what we've tried. So we'll have a visual affordance model that the agent applies when it sees an object, and it will be anticipating where, in this case, where grasping should happen. And then it'll leverage this as a prior to guide its own interactions and trials to learn a policy to do functional grasping. And if this goes well, what we want to see come out is faster learning. So get to a policy that's successful with less batting around of this object on the table, better grasping, holding it firmly and stably, and most importantly, generalization to new objects, so that even if affordances were learned on objects 1 through n, object n plus 1 with any sort of shared visual characteristics will still have a useful prior through the visual affordance model. And that's actually something to emphasize about this approach, because it's object-centric in what is passed to the agent as opposed to hand-centric. It's more about what is understood about the object it's looking at, such that it can draw its behavior towards those parts. So let me say briefly in our a handful of minutes here how this approach works. So first, train a visual affordance model. And now we've kind of taken a step back in the visual realism here of my objects, because now we're working in a simulator. Mujoko with an adroit hand model. But here we can still learn the visual affordances of objects like these to know where they're likely to be grasped, and then generalize it to new objects. Okay, so we haven't seen an axe, but it shares some visual properties with pans or knives, and so we expect where the grasp would be. So take that visual affordance model, and now related to what I showed you kind of in the first half of the talk, we're going to connect this to a policy learner in which we are encouraging the policy to choose actions that will bring it close to those regions that are the high probability for visual affordance. So quite simply, we'll just have a reward that not only says, it's good when you get something off the table, but also rewards the agent for having parts of its hand near that afforded region. And the afforded region is predicted from the pixels of the image. Okay, so that's the basic idea, trying to put these ingredients together. We call it graph for grasp affordances. And I'm going to show you kind of the training progression here for 6 different objects. So we learn a single policy for all objects. Here is its learning happening with any of these particular 6, where earlier iterations, it's batting and fiddling around. But because it has this guidance of likely human-used parts, it is successfully zooming in on those in order to start picking up the objects. And in fact, that is the benefit we're seeing so far. and speed and sample efficiency of learning. Here, this is graph, the approach I'm just showing you in blue, and two pure RL baselines that are like ours in terms of just trying to learn policy from experience of how to do grasping, but unlike ours, do not have this visual prior. So COM, center of mass, it's just guiding it towards trying to get to the center of mass, and red is absolutely no prior, it's just rewarded for getting the thing off the table. And so basically, in 10 hours of robot time, we can get to the level of accuracy that would take 30 hours of robot time from such baselines. So then let's just see the behavior. And now I'm showing the baselines up here that I mentioned, which are these pure RL methods that lack our prior. But I'm also adding a comparison point, which is the bottom left. This is, I would say, a state-of-the-art method for learning from people, but in this case, learning from people in a very direct way through state action pairs or demonstrations in which someone has used the VR headset to and a glove, a motion glove, in order to teach through example how you pick up objects. And that's DAPG. And then ours is in the bottom right. So now I'm going to play it, and this will give a sense of how well these different methods are working. The ones on the top, we already, know the punchline that their success rate is much lower. The DAPG in the bottom left has a quite reasonable success rate, but less efficiency in that it's trained specific to each object in order to get this behavior. And so overall, as the results show in total, this graph approach is able to leverage what it's learned from people to learn faster and better policies. Okay, and that plays out through both objects that the agent has seen, meaning for this visual affordance learning. Those are the contact DB objects. This is a data set of 3D objects. Those are the success rates are in blue, but also for objects it hasn't seen. And this is where we're forcing that generalization to understand where grasping is likely to succeed, even for a new object that has some visual relationship to the others that we're seeing. Okay. All right, so before I close, I have 2 more slides that are really just teasers because there's parts of our work that are brand new that I'm also excited about, but not having time to talk about today. So I'm going to give you 1 slide pointers to 2 of these. And they fall more, if you remember the beginning of my talk, they fall more in this realm of navigation and recognition. The first of the 2 is multimodal audiovisual navigation. And if you're interested, play this video online with headphones, and you'll see how we've added sound rendering capability to 2 of these sets of photorealistic environments that can be used for reproducible RL embodied AI studies. So you can play sounds now in Matterport 3D so that you can tackle things like audio-based navigation, such as finding the smoke alarm. And the other one is our ongoing work with embodied visual navigation, in which we've developed exploration strategies and navigation policies that are able to infer beyond what they see in the map. And that's the idea of our occupancy anticipation. And this approach won the Habitat Challenge this year. All right, so I'll stop here. I've talked about people watching for agent learning through the environment side as well as the object side. And the work I covered today is thanks to the folks you see at the bottom here, Tushar, Yanghao, Christoph, and Priyanka. Be glad to have your comments and questions. Thank you.
Well, thank you very much, Kristen, for a great talk. I'd like to, so if anyone has any questions, please feel free to indicate on Zoom.